Hello, my name is Mugil Shanmugam and welcome to Agora Math Circle's MathCounts training. This is video 1 of a 12-part series in which we will teach you everything you need to know to succeed in MathCounts. And by the way, my name is Mugil Shanmugam in case I didn't mention that, but let's get right into it. Overview of the course. Welcome to Agora Math Circle's MathCounts training. In this course, you will learn all about America's nationwide middle school competition called MathCounts. Our course aims are simple: to put you in the best position you can be to succeed in MathCounts. Through our regular videos, we will introduce you to the different topics and problem-solving skills you need to succeed on the MathCounts exam. Our course will consist of 12 videos posted on a weekly basis. Please check our YouTube channel, Agora Math Circle, for these videos. We strongly encourage you to subscribe to this channel so you can get notified when we drop a new video, and it also helps us post more videos and cover different topics. Please do subscribe, it really helps a lot. Videos will be posted on a regular basis. This could be weekly or bi-weekly, it hasn't yet been decided, but we will post them regularly. And this is our YouTube channel. I just put a screenshot of it in there, so please do subscribe, it really helps us. Material used in this course. So the material for this course is taken from two books, 20 problem-solving skills and 20 more problem-solving skills from the same author, Jane Chen. So all credit goes to them. So let's get into Session 1 topics. Session 1 topics. Today we will be covering the following: Introduction to MathCounts, Magic Squares, and LCM and GCF. And the subtopics under this for Introduction to MathCounts is what the competition is, the format of different rounds, etc. For Magic Squares, Magic Square formulas, sample problems, etc. For LCM and GCF, definitions, theorems, sample problems. So let's get right into it. What is MathCounts? So MathCounts is a nationwide math competition for middle school students, allowing kids to explore their passion for mathematics at a young age. Many schools have a MathCounts program which students practice for the competition. These schools also have a school MathCounts competition, the first stage of qualifying. As of 2021, the round after the school round is a chapter round, followed by the chapter invitational round, the state round, and finally the national round. The top student of each school and the top 20% of a chapter advance to the chapter round. After this, the top 5 students from each chapter and the top 10 students in the state after these top 5 students advance to the state round. The top students from each state go to the national round. And please note that due to COVID-19, next year this will all change. This is not by any means permanent. But this is just something that's good to know. And don't get too caught up in the statistics of who advances and who doesn't advance. That doesn't really matter. All that matters is you try your best and you're trying the hardest that you can do. The whole goal of this is to just improve yourself. So MathCounts round format. The sprint round focuses on speed and accuracy. Students have 40 minutes to compete and do some math problems without a calculator. The target round focuses on problem solving and mathematical reasoning. Students receive 4 pairs of problems and have 6 minutes to complete each pair, assuming the use of a calculator. The team round focuses on problem solving and collaboration. Students have 20 minutes to complete 10 math problems, assuming the use of the calculator. Only the 4 students on a school's team can take this round officially, and this is only national level for 2020 to 2021. This could change next year, no one knows. And the online practice competitions will also have a team round so you can practice. And the countdown round focuses on speed and accuracy. Students will have a maximum of 45 seconds per problem without a calculator. This round is optional at the school, chapter, and state level, but it's mandatory at the national level. And I got all this information from the MathCounts websites, and I put the link there, so feel free to go check it out, browse it. It's a really good resource, and you could learn a lot about the different competition formats that you'll have to face during your time MathCounts. Interested in MathCounts? Well, ask around the school and see the options that are available for you to participate in MathCounts. Now, I know that some schools don't have a MathCounts club, so don't worry about that. What you can do is you can talk to a teacher and gather a group of friends, and you can try to start your own MathCounts competition, or your own club, I mean. And using this, you could then enroll in the competition. And the information for creation of a MathCounts program at school, as well as information for coaches, you can find all this on the MathCounts website. I put a screenshot of the MathCounts website there. So if you go to that link, there's lots of information on how you could start your own MathCounts club and participate in the competition from your school. But please do know it's only offered by the school, so you need to do it through your school. So let's start out with magic squares, our first actual topic for this session. So by definition, a magic square is a square, n times n. That just means there's n rows and n columns. N is the same number, with order n, and n squared numbers on the grid. So basically, let's just say that n is equal to 3. Then you have 3 rows, 3 columns, and 9 numbers in the grid. And the example there also has this: 3 rows, 3 columns, and 9 numbers in the grid. Now, the important thing about a magic square is that each row, each column, when you add it, you get 15. As we can see in this magic square, 2 plus 7 plus 6 gives us 15. 9 plus 5 plus 1 gives us 15. 4 plus 3 plus 8 gives us 15. And in the same way, if we add up the columns, we get 15. 15 is called the magic sum in this case, which is denoted by the letter S. And as you can see, this magic sum, we can use it in different formulas to find out the different numbers in the grid. But for now, just know that the S stands for magic sum, which is the sum of every single row and column. They will all be the same number. That's why it's called a magic square. So there are some quick and easy formulas we can use to find the sum of magic squares. If a magic square of order n, this means that it has n rows and n columns, begins with the number m, and m is followed by consecutive counting numbers, the following formula can be used to calculate the magic sum. S is equal to n into 2m plus n squared minus 1 over 2. The formula is right here. So what this basically means is if you have, let's just say, a magic square, 3 by 3, and the first number is 1, then it's 2, then it's 3, then it's 4, then it's 5, then it's 6, then it's 7, then it's 8, then it's 9. If you have something like that, you can use this formula to calculate it. But if m is equal to 1, so in the example I just gave, the first number is 1, so m is equal to 1. M is the first number in the box. So if m is equal to 1, you change the formula to n into n squared plus 1 over 2. And the way we get this is if we plug in m equal to 1 into the original formula up here, that's how we get this new simplified formula, which only applies if m equal to 1. The first entry in the magic square is 1. So now that we know these basic formulas, let's move on. For some of the following magic squares, you could also use the formula that C, so C is one of the entries in the magic square, is equal to S over 3. So magic sum over 3. And it's also equal to A plus B over 2. And A plus B are also some numbers in the entries in the magic square. So in this case, you can see C right here. C is actually in the magic square, it's in the center. In this case, you can see A, C, B. A and B are also 2 entries. So if we know A and B, we can find C because we know that A plus B divided by 2 will give us C. So that's just a quick and easy formula you can use. But please note, it only applies for these specific formations. So you have to be in this particular formation. It has to be C in the middle, A, B, and C in the middle, or A on the top, B on the bottom, and C in the middle of them on a diagonal root. So it has to satisfy one of these following formats. And you can also use the same formula, C is equal to A plus B over 2, if it looks like this. C in the top left, A in the middle on the right, and at the bottom, B in the center. So for this format also, you can use C is equal to A plus B over 2. And don't worry, we will be doing some sample problems using some of these formulas, but for now, just try to know these formulas. Obviously, memorizing these formulas really helps, but just try to first understand them and how you could apply them. So this would be a good time to maybe come up with your own practice problem, maybe try to draw up these grids and try to figure out how it works. Okay, now let's move on to magic triangles. We'll come back to magic squares and some sample problems, but first I just want to quickly go over magic triangles because these are also very helpful. So magic triangles are basically a magic square, but they're a triangle. I mean, that was pretty obvious, but you know what I mean. So in a magic triangle, basically there's the same number of numbers or entries on each side of the triangle. And the example I've given you right here, there's 3 numbers on each side if you count it. And the sum of each side is 9. 9 is your magic number, magic sum as you could call it. So that is how a magic triangle works. Similar to a magic square, it's just a triangle. Now, K is equal, this is one formula that we would use, and K is equal to the sum of the numbers at the vertices. So the sum of the numbers of the vertices, what I mean is you see the 1 at the top, the 3 at the side, and the 2 at the side. 1 plus 3 plus 2, that's 6. 6 would be k, the sum of the numbers of the vertices. They'll often refer to this on the MathCounts problems. So remember, when they say sum of the numbers of the vertices, you're adding the numbers of the vertices. And in this case, it's 6, in this one only. Now, and s is equal to the magic sum, as I said before, in this case it'd be 9. And with a, b, c, d, e, f. So these, I'm just always using letters. These letters are actually representing the numbers on that triangle. So here, 1, you could say that it's a. 5 is b. 3 is c. 4 is d. 2 is e. And 6 is f. So it's just up to you. I'm using numbers, letters, because that's easiest to represent in formula form. It's up to you. But this is just how you generally represent it. And the order of A, B, C, D, it doesn't really matter as long as you're uniform with how you do it. So you could start with A equal to 6, but then make sure you're going in order for B, C, D, E, F. So the formula is 3s. So 3 times your sum is equal to A plus B plus C plus D plus E plus F, in parentheses, plus K. What this says is basically 3 times your magic sum is equal to the sum of all the numbers on the magic triangle plus the sum of the vertices. So remember, we found that k was equal to the sum of vertices. So that's how we got this formula. Basically, if you add all the numbers on this magic triangle and add the sum of the vertices, you'll get 3 times the sum. This is a very handy formula. You'll often get magic triangle problems, and with this formula, if you have a sum, you can find some of the vertices. If you have the vertices, you can find some of the sum. You can find the sum, and etc. So it's very useful. This is a very good formula to have in your toolkit. So sample problem 1. The whole numbers 11 through 19 are arranged in a 3 by 3 square. So you could say a square of order 3. So that the sum of the rows in each row, column, and diagonal are the same. What is the common sum? And this is from the 1997 MathCounts State Sprint. So I'll give you a little hint on this one. When they say that the sum of the numbers in each row, column, and diagonal are the same, that means they're referring to a magic square. So this is a magic square, and 11 through 19 are consecutive counting numbers. So we learned a formula regarding this. So take a minute here to pause the video and try to solve this by yourself and see if you can figure out how to do this using the formulas that we learned earlier on in the video. Okay, hopefully you took a second to pause and try it out. It's helpful for you. So let's move on to the solution. So we need to use the formula for consecutive counting numbers as entries in our magic square with m equal to 11. So that's what I meant, because we have consecutive counting numbers 11, 12, 13, 14, 15, 16, 17, 18, and 19. So these are consecutive counting numbers. Now, without we have these consecutive counting numbers, if we put them in the magic square, we can use our formula that we learned with m equal to 11. The first number we put in the square is 11. So if we go back to that slide, in this law, the first law on the left, that's where I put my 11. So we have this formula, n into 2m plus n squared minus 1 over 2. And as you can see, I solved it out here. So 3 is your n here, because remember, there's 3 columns, 3 rows. And 2 times m is just 2 times 11 plus 9 minus 1 over 2. And when you calculate this out, you get 45. So this is how we found our formula. So remember, 2m is 2 times 11 plus 9, because there's 3 rows, 3 columns. When you square that, you get 9. Minus 1 all over 2. When you calculate that out, you get 45. 45 is your magic sum. Now, what this basically means is when you add up each row, each column, you'll always get 45 as your magic sum. S is equal to 45. So that was basically how we apply one of the formulas we learned earlier on, and we managed to apply this to this magic square that we just learned about. So let's move on to the second sample problem. The digits 1, 2, 3, and 9, well 2, 9, are arranged 1 per circle in the triangle shown, so that the sum of the numbers in the 4 circles along each side of the triangle is 17. What is the sum of the numbers in the 3 circles at the vertices of the triangle? Okay, so this is one of the magic square triangles that we learned about, the magic triangles. So to solve this, we need to use that formula we learned about. The one with 3s is equal to the sum of all the entries plus the sum of the vertices. So using that formula, you can solve this one. So I'll go over the solution in a second, but this is a really, really good place to pause, take a quick break, and maybe solve this problem for yourself so you know how to do it and you can apply your own knowledge. So take a second to pause. Okay, hopefully you guys paused me and did the workout, so let's go into the solution. Let the sum of the numbers of the vertices be k. This is what we did back then when we actually came up with this formula, that the sum of the vertices is k. So one number here, one number here, one number here. The edges of the triangle, those numbers, when we add them up, we get k. This is what we're trying to find. S can be the sum of each side. So S is our magic sum that we're trying to find. That we already know. We're trying to find k. Using the formula, what we know, 3 times S is equal to A plus B plus C plus D plus E plus F plus G plus H plus I plus K. Now you might be wondering, why did you add the G, H, and I? Well, see, the formula that we used before was for a triangle, but it was for a triangle with 3 entries on each side. That's how we came up with it. But now we have 4 entries on each side. If you come back here, there's 1, 2, 3, 4. 4 entries on each side. So because of that, we need to add a few more variables in there to make the calculation proper. So that's why I did this, because now I can count for all the entries on the triangle plus k. So our magic sum we figured out was 17 because that was given to us in the problem. You always want to underline information that helps you, or maybe circle it, because this information can come in handy, like the magic sum right here. So 3 times 17, because 17 is our S, is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus k. So now we have a basis of a linear equation, an algebraic equation, one that shouldn't be too hard to solve. So now when we calculate this, we get 51 is equal to 45 plus k. Now we're trying to find k, so if we subtract 45 from both sides, we get k is equal to 6. So basically what that's telling me is when I add this top one, this circle, and this circle, I will get a total of 6. So our k is equal to 6, and that's the answer here. The sum of the numbers in the 3 circles at the vertices is equal to 6. Okay, so now let's move on to the greatest common factor and the least common multiple. Sorry, the least common multiple, that heading is a little obscured by my camera, but the rest shouldn't be too bad. And I'll be explaining it either case. So, the greatest common factor and least common multiple, to understand that, first we need to understand what is a multiple and what is a factor. So if A is divisible by B and B is not equal to 0, B is a factor of A. For example, take 6 and 3. 6 is divisible by 3. Therefore, 3 is a factor of 6. I'm using A and B as a substitute for some numbers. If this confuses you, I invite you to replace A and B with maybe 6 and 3, 2 and 4, whatever helps you, and you can try to solve it that way, or think of it that way, because that's helpful for some people. That's just your personal preference. Now, if A is a multiple of B, if B is a factor of A. So what that means, if B times some number will give you A is a multiple of B. In this case, 3 times 2 gives you 6. So 6 is a multiple of 3. Now, a common factor is the factor of all numbers in a set. So if I gave you like a list of 3 numbers right now, and you found factors of all of them, the common factor, the greatest common factor, would be the biggest factor that they all share. So one way some people like to do this is like they write out all the factors, then maybe they circle the factors that are common, and they find the biggest one. A common multiple is the multiple of all the numbers in the set. So if I give you 3 numbers and you found a multiple that they all shared, that is called a common multiple. So that is, you can multiply them by different numbers and you get the shared number, a multiple. Now, the largest integer factor of a group is called the GCF. For example, the GCF of 4 and 6 is 2. So 2 is the biggest factor, or the biggest divisor of 4 and 6 that will divide them evenly. We always want to remember the GCF has to be an integer, so you can't use 0.5 or 0.766. It has to be a flat integer, 1, 2, 3, so on. So that's how, or it could be -2, but it has to be an integer. So that's how we'd find our GCF. And you might look at this notation that I'm using when I give the example. You can see some parentheses around the 4 and the 6. Parentheses are actually the notation we use to find when we're finding GCF. So if there's parentheses around two numbers and the question is related to GCF, that means we're asking you to find the GCF of those two numbers, the numbers in parentheses. So make sure parentheses are for GCF. Now, the smallest integer multiple of a group is called the LCM. For example, the LCM of 4 and 6 is 4 and 6, and that would be 12. As you can see, I wrote 4 and 6 in brackets here. Brackets represents LCM, and you would find the LCM of the numbers in between the brackets. And in this case, it's 12, because 4 times 3 is 12, 6 times 2 is 12, and this is the smallest multiple that they both share. So that's how I found my LCM, and I found my GCF earlier. So remember the notation, it's parentheses for GCF and square brackets for LCM. So that's something to keep in mind, but other than that, this should be a pretty simple review. Theorems related to GCF and LCM. Any factor of the first theorem is any factor of the GCF of two numbers is also a factor of the two numbers. So what this is basically saying is if you have two numbers A and B, and you find their GCF, now the GCF will often have its own factors. Let's just say that the GCF is 6. Well, 6 has factors of 2, 3, 1, and 6. It has 4 factors. So these factors are also factors of A and B. So basically what this is saying is if you have two numbers, their GCF, and if that GCF has factors, the factors are also factors of A and B. And again, if this is, you could always substitute A and B with two numbers. That may help you visualize this a little better. The second theorem is if the LCM of two numbers is C, multiplying the two numbers by n will yield an LCM of n and c, provided that n is a positive integer. So what this is saying is if you have two numbers and you found their LCM, you can multiply those two numbers by one number, and if you multiply the LCM by the same number, you can find the LCM of the two new numbers. So let's just say that you can have 2 and 3. The LCM of 2 and 3 is 6. We know that, right? But if I multiply everything in this set by 2, so I have 4 and 6. The new numbers I'm finding the LCM for are 4 and 6. And the LCM of this is 12. I could have also found that by just finding the original LCM, which was 6, multiplying it by 2, and I get 12. So that's the second theorem that we can use. The third theorem states that A times B is equal to the GCF of A and B times the LCM of A and B. And using this, we can also find that the LCM of A and B is equal to A times B over the GCF of AB. There isn't a whole lot to explain here. It's just a simple formula where you're basically finding the GCF and the LCM, and if you know some parts of it, like if you know what the product of A and B is and you know the LCM, you could find the GCF, and so on. It's just some relationships that you should keep in mind when you're solving. And again, use some normal numbers like 2 and 3 if A and B gets a little confusing. Theorem 4. The GCF of three numbers is equal to the GCF of the product of the first three numbers and the three numbers. This applies for the LCM as well. So as you can see, underneath that, I've given some examples. So if you have three numbers A, B, and C, you can find the GCF of A and B, and then find the GCF of C and the GCF of A and B. So let's just say I found the GCF of A and B. The GCF of A and B is X. So then after I find that, I can find the GCF of X and C to find the GCF of all three numbers. So that's a quick shortcut you could use. And the same thing applies for LCM. So if I find the LCM of A and B, and that's Y, then I can find the LCM of Y and C, and that's the LCM of all three numbers, A, B, and C. So yeah, those are just some simple theorems. Theorems continue. This is our last theorem, and this theorem deals with finding the LCM and GCF of two fractions. So if you want to find the LCM of A over B and C over D, then you can use this formula, which is, so basically this is equal to AC, so A times C, over the GCF of AD BC. So basically this is just a quick formula you can use if you find the product of the numerators and you find the GCF of the cross multiplication. And this is also equal to the LCM of AD BC over BD. And for the GCF, it's the GCF of A over B, C over D is equal to the GCF of AD BC over BD, which is equal to AC over the LCM of AD BC. Now you can notice some patterns in here. It's pretty obvious. If you look at this, it says AC over GCF of ADBC. Here we have the same thing, except the GCF is switched with an LCM. And similarly here, we just switch the LCM and the GCF. So if you remember one formula, you can practically remember the other. It's just, they're kind of very similar. It's just a little substitution of LCM and GCF. Yep, but those are just some simple formulas you can use to find the GCF and LCM of fractions. You could always do it normally. This is just a simple shortcut that the author of the book used because that helped her. And this may help you too. I'm just providing it out there. Ultimately, you just do you. Okay, so here's our first sample problem. 2 traffic lights turned red together at exactly 5 p.m. One light is on a 30-second cycle from red back to red, while the other is on a 48-second cycle from red back to red. At what time will they turn red together? Give the exact time, including seconds. Okay, so for this one, whenever you hear about like these cycles of like 30 seconds and 48 seconds, whenever they're asking you anything about that, you should always think that this is an LCM problem. You need to find the LCM of these 2 cycles. So one cycle is on a 30-second cycle, and the other light is on a 48-second cycle. So try to find the LCM of these 2 numbers, and that will give you an idea of when they're going to sync up and have the red light at the same time. So now's a really good time to take a pause and solve this problem for yourself. So go ahead, give it a go. Okay, I really hope you guys tried that one. So let's go into the solution. Okay, to solve this problem, we need the LCM of 36 and 48. To do this, first prime factorize both the numbers and then find the largest power of each common prime factor. Multiply this to find the LCM. So this is one quick trick you can use to find the LCM. Prime factorization is basically breaking down a number into its prime factors. So for 36, you can break it down into 2 squared times 3 squared. For 48, you could break it down into 2 to the 4th power times 3. So these are prime factors because 2 and 3 don't have any factors of their own other than 1 and their self. So now that I found the prime factorization, the LCM, if you want to find it, is you simply find the common factors. So I'm going to look for the common factors. Well, both of them have 2, both of them have 3. So both of these are common factors. Now I find the highest power of those common factors. Well, here the highest power is 2 to the power 4, and for 3, the highest power is 3 to the power 2. So when I multiply that together, I get their LCM, which is 144. This means every 144 seconds, the lights will turn red together. Sorry, that's a typo. I meant to say red, but yeah. Now, 144 seconds, if you remember, each minute has 60 seconds. So when you do the math, you get 2 minutes and 24 seconds are there in this 144 seconds. So by adding this to 5 p.m., we get 5 p.m., 2 minutes and 24 seconds. So this means at 5 p.m., 2 minutes and 24 seconds, the lights will turn red together. And if you look back at the original problem, it said that they turned red together at 5 p.m., so that's how we got the 5 p.m. And I simply added the time it takes for them to sync up again to that to get 5:02:24 p.m. So yeah, that's your answer. Alright, sample problem 2. 2 natural numbers have the GCF of 6 and an LCM of 36. That says 36 in case you couldn't read it. If the sum of the 2 numbers is 30, what is the value of the smaller of the numbers? Okay, so here, this is one of the problems where you want to use those relationships that we found in our theorems. Remember, we found how LCM relates to GCF, which relates to the product of A and B. So try to use that formula in this case. Try to apply it and try to figure out how you could solve for the value of the smaller of the numbers. So pause and give it a go. Alright, I hope you actually tried it, and let's go into the solution. So for this problem, we need to use a theorem that states A times B is equal to the LCM of AB times the GCF of AB. So this is what I was talking about, the relationship between the product of A and B, the LCM, and the GCF. So to use that, we would use this formula. Now assume that the 2 numbers are A and B. These are just 2 variables that we're using in this case. In that case, A times B is equal to 36 times 6, which is equal to 216. Now you may be wondering, how did you get 36 and 6? Well, in the problem, they told us that the LCM is 36, the GCF is 6. And remember our formula. A times B is equal to the LCM times GCF. Well, if we have the LCM and GCF, we can just multiply them. So A times B in this case is going to be equal to 216. We found that using our formula. Now, we also know that A plus B is equal to 30. Now, they can only be like a very limited number of numbers to actually satisfy this condition. So we can just use guess and check here. That would be probably the best way to go with such a small group of numbers to work with. And the only two numbers that satisfy this condition are 12 and 18. And as I said, you can use guess and check to find this. The smaller number out of 2 and 18 is, out of 12 and 18 is 12. So 12 is your answer for this problem. And again, so the way we found that was we just used our relationship, and then we moved on from there, and we used guess and check to find the only numbers that fit in this solution region that we have. So the answer is 12. Okay, thank you for watching this video. I really hope you enjoyed it, and I hope you learned something about MathCounts. Please like and subscribe if you enjoyed the video. Leave a comment with any questions you have down below. We'll be more than happy to answer you and help you. Stay tuned for the next video. That's going to be coming out soon. Subscribe, hit the bell so you know when we're uploading a new video. Thank you for watching and have a nice day. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!